Hello everyone, welcome to this NPTEL course on Advanced Reinforced Concrete Design. We're going to start with a new module 9. We are entering into the week 12 of this course. In this module, we are going to discuss about serviceability and bond and then anchorage issues related to reinforcement. So this is a quick overview of what we're going to discuss in this module. First, we will introduce what is serviceability and a lot of factors that affect serviceability, but the two important aspects that affect serviceability are deflection and cracking. We will discuss about this in detail, and then we will also talk about what is bond and what is development length. How do you make sure that the bars are anchored and it's not going to slip? So those things that we will discuss. So the first part of this module is introduction to serviceability. We are going to focus mostly on deflection in this module. In the next part of the module, we are going to discuss about crack width, and then we'll talk about bond and anchorage in the last part of the module. Okay. So with respect to this part, what are the expected learning outcomes? The student should be able to explain the need to check for limit state of serviceability after designing the structures by limit state of collapse. So what does it mean? Usually in RC design, we design for limit state of collapse and then we check for serviceability. So we'll see why we need to check for limit state of serviceability. And we have in deflections short-term and long-term deflections. The student should be able to differentiate between what is short and long-term deflection. And the student should also be able to state what are the factors that influence this short-term and long-term deflections. And we are also going to go through an example problem. And after going through the example, the student should be able to calculate for any given cross-section or a member what are the short-term and long-term deflections for RC flexural members. Right. So we have discussed this in depth when we talked about design philosophies, how it evolved over a period of time, right? So the modern limit state design approach in reinforced concrete design, most of the structure members, not always, we design for limit state of collapse. That is, we worry about the strength, and also we make sure that the other stability issues are taken care. We design the system such a way that then we go ahead and check for serviceability limit states. Okay, so why is it we need to worry about that? Because it's going to disrupt the functioning or use of the structures. The structure may be safe, it may have adequate strength, but it may be in a condition that you may not be able to use the structure if serviceability limit states are not satisfied. So it is going to disrupt the use of structure. Okay, so why is it we need to worry about limit state of serviceability? As you've seen, when people used working stress method or even ultimate load method, you end up with a very larger cross sections. And then because we were using working stress method, we were limiting the stresses to be within the elastic regime. So to satisfy the design requirement, we end up putting bulkier cross section. So when you do that, the serviceability performance was automatically taken into account because you're limiting only your stresses to fraction of what the material strength is. But as the design philosophy evolved, nowadays we are using limit state method. So the adoption of limit state design, and also nowadays we are using very high grades of concrete and steel also. We have seen that the grades of steel has increased quite a bit, right? From FE 250, FE 415, FE 500, FE 550. Now we have FE 600 also is available in the market. So because of adoption of this limit state design approach, where we are designing it for nonlinear stress strain curve behavior, that what we are using, we end up with more efficient cross section. So, or in other words, thinner cross section, and we are also allowing higher stress levels in the material. So because of that, if you're not careful in your design, we can have larger deflections, crack widths can be higher, and also you may have wave vibrations and the stress level in the steel may become higher. So if you're not careful. So it's not that limit state practice is not good, but we have come up with a more efficient design philosophy, and we are also using high strength material. If you are not careful, then you may violate the deflections and crack width requirements. The structure also may be having vibration issues if you are not careful in our design. Right. So let's say limit state design. Then we have said first limit state of collapse. So we designed the section dimensions and reinforcement and where to put the reinforcement. All these things that come from strength requirements. And then we also check for overturning, sliding, buckling. All these things we check for limit state of collapse to make sure that these failure modes do not happen. Right. Then once we finalize your cross section dimensions and arrangement of your structural members, then we go ahead and check limit state of serviceability. Now, what is the limit state of serviceability? We have to check for deflections. Okay, if the flexural members are going to undergo large deflections, then also if you have cracking like this, then it will affect the serviceability of the particular structural member, right? We can also have cracking, maybe also due to corrosion like this. Okay, these are column members. Because of the corrosion, you have this kind of cracking. So that also we need to be careful. And durability, we discussed this in depth in the part 3 of the module, part 3 or part 4 of the module. We discussed what are the factors that influence the durability of reinforced concrete system. Again, if you are not careful, you may end up with this kind of corrosion, and it may affect the serviceability of the particular structure, which we have already discussed how to improve the durability of reinforced concrete systems. And vibrations, again, in long span bridges, you must have seen, if your dimensions and arrangements are not proper, like the one that we are seeing in this image, you can see that for long span structures are more prone to vibration because they're very slender. And if you're not careful, you can, again, vibration of the structural system may affect the performance and usability of the particular structure. So we need to check. So in this, we are going to focus mainly on deflection and cracking, and durability we have already discussed. Vibration is a topic in itself, so that we are not going to cover. We are going to focus on one of the two most important things in terms of limit state of serviceability. Those are the deflection and cracking. Now let's say what is the serviceability limit state. Okay. So as the definition says, serviceability limit state is defined as the state of design beyond which the structural system is going to lose its serviceability and it cannot be operational for the actual service load that is subjected to. If you have huge deflection, then while you're walking on the slab, you may feel uncomfortable, right? Similarly, when you put a equipment and if the floor is deflected, then the equipment may not be able to function properly, right? So these are all some operational issues. So that is going to, the system is going to lose its serviceability and it will become inoperational, right? So let's see what are the different limit set of serviceability. So we have said main deflection is, in deflections, we need to know how to estimate the short-term deflection that are happening because of dead and live loads that are immediately the structural system is seeing. And we also discuss in the material chapter, concrete undergoes creep, shrinkage. If you're talking about a pre-stressed concrete system, the steel also undergoes something called relaxation. All these things, because of that, the deflection will keep on increasing over a period of time. So those are called as long-term deflections. Again, that we need to be careful. Okay, so here in this chapter, we are also going to discuss about IS code provisions, that is IS 456 provisions, how we can use these provisions to make sure that limit state of serviceability is accounted for in our design. Right, when it comes to crack width, of course, we need to make sure that we have to estimate the crack width under service loads and make sure that they are within certain acceptable limits. Usually, we do not go more than 0.3 millimeter in our design. The crack widths cannot exceed 0.3 millimeter under service loads. And we will also talk about how we can use IS code provisions to check the crack widths at different cross sections. Right. So in this, now in this part of the module, we are going to focus only on the deflection, and where we are going to focus on short-term and long-term deflections. Right. So now before we proceed, what is short-term and what is long-term? How do we check? Let's see, why do we really need to do this deflection check? Right. So if you look at class 42 and 43 of IS 456, In fact, it says that if you follow the provisions in IS 456, we don't need to require any explicit check on deflections or crack width for all normal cases, provided the LYD ratios that what we have adopted for structural members, span to effective depth ratios, has to be within certain limits. We will look at what are those limits. Usually LYD ratios are, it is given some limits, 20, 26, like that, right? So those, if you follow that, automatically the code says that your deflection performance will be guaranteed. But and also the spacing of the flexural reinforcement for crack control are complied with. Okay, so if you satisfy spacing requirements for steel, if you satisfy limiting LBD ratios, then automatically it is understood that your deflection and crack width performance will be taken care, and you don't need to do any explicit check. But it is not always the case. Okay, so, and again, why? So, even though we do that, so the minimum depths indicated by these L by D ratios may not be adequate for certain sequences of shoring during construction. Again, we have seen that in residential construction, particularly, dead load can be quite significant, right? So, similarly, sometimes, depending upon the span of a bridge, dead load can be quite significant. If you are removing your shoring improperly, then this LBD ratios may not be adequate. Okay, whatever that the code suggests. Okay, and also one of the another important aspect is when you have a large live to dead load ratio, right? So in that case also the pattern loading will come into picture. Then your LBD ratios, whatever that is given by the code, may not be applicable. So that's why these LBD ratios are if you're using those LVD ratios, then your live load to dead load ratio also should be within a limit. And also we need to make sure that it has to be the structural system has to be showed, or they have to be supported during construction for a stipulated period of time, right? Okay, sometimes design engineers, they exceed the provisions that are given in your code, or sometimes we also violate the provisions. In those cases, if to make sure that we are not violating the performance requirements, then we need to check for your serviceability checks. And for non-standard design, to check serviceability when the code limits are not complied with, then we need to go ahead and do the deflection checks. Explicitly, we need to check and make sure that the deflections are within the allowable limit. Now, we may also have some special structures where limits to deflection and crack width are of very particular importance, because here you will find that the deflections are usually, we will have some limits that we will discuss about that. It is L by 350, L by 250, like that. So, but these are valid for certain set. But if you're if you're going for a very special kind of structures and your deflections has to be very, very stringently controlled, then you have to go and do explicitly check for your deflections, calculate the deflection, and make sure that it is within the acceptable limit. Right. So again, why do we need to limit the deflections? First of all, when you see the slab elements or beam elements undergoing large deflection, then it's kind of instills some fear for the occupants and visual appearance. Usually, when the deflection becomes more than span by 250, then it is very perceptible to human eye. Then it kind of instills some fear for the occupants who are using the particular facility. And when your slab, for example, when it is deflecting, then what it can do? It can damage the partition walls, because partitions are non-load bearing element. And so if the slab is deflecting and if the load is getting transferred to those partition elements, then it can lead to the damage or cracking of these partitions. And then your doors and windows may not function properly. So it will get jammed, and we will not be able to use this elements properly. And most important thing is you may have disruption of the function of the facility or the structure. Why? If you are having sensitive machinery or equipment installed in a particular floor, and if you are having high deflections, then the machine and equipment cannot function properly. Okay. In fact, in machine foundation, you will have some tolerance that will be specified. Deflections has to be within certain limit. Okay. And in roof, we have to be even more careful. If roof is deflecting high, in fact, roof deflection limits have to be more stringently followed. The reason is you may have ponding of rainwater. Then the ponding of rainwater, if it is going to stay there for a long period of time, then you'll have more deflection. So then in the subsequent rain, more water can accumulate. So it will become a cumulative cycle, and you may lead to collapse of the roof as well. So again, ponding of rainwater on roofs also can be an issue. And if you're not careful, again, it can lead to, again, large deflections in serviceability problem can lead to damage of other structural elements as well. So that also we need to be very careful. This is the reason we need to limit deflections, right? Now, how do we calculate it, and what are the challenges that are encountered in calculation of deflections for reinforced concrete flexural members? So, the deflections we are looking at only majorly we are looking at floor slab element and flexural beam elements, right? We're not looking at lateral deflections of the frame. So that is a separate topic in itself. We are looking at from serviceability point of view, what are the deflections in horizontal members. Okay. Now, what are the deflections? How do we calculate? So we know from structural analysis, let's say for an uniformly distributed load for a, let's say, beam that is simply supported beam, which is subjected to, let's say, a load like this. What are the deflection equations? You must have studied. Delta is pi by 384 W L power 4, right, by EI. Now, what is EI? We have done moment curvature analysis. EI is called flexural rigidity. Okay. So, this flexural rigidity, we cannot estimate it accurately. The reason is deflection is a member level property. What we have done in your flexure moment curvature analysis, sectional analysis. So, when you have sectional analysis in your moment curvature, when you take the slope of moment by curvature, then you get your flexural rigidity, and the flexural rigidity will keep decreasing depending upon the amount of your moment that you're applying in the cross section. That we know. But now deflection is a member level property. So what is the flexural rigidity that we will use in our calculation? There are uncertainties in predicting the flexural rigidity, and the flexural rigidity is also going to vary as a function of applied load, right? So this is one thing. So another thing is you have varying degrees of tensile cracking in concrete. Right? Now, for example, this kind of a let's say I'm taking this kind of a beam which is simply supported. Then here for a simply supported case, where you will have cracking, you will have cracking wherever the moment is exceeding. First, it will happen in the middle. Right? So the degree of tensile cracking of concrete is going to be. But when you have a beam which is part of a continuous system, then you will have cracking both at the support locations at the top and at the midspan location at the bottom, depending upon your loading. And also reinforcement along the length of the member is going to be not constant. So you have varying amounts of flexural reinforcement. In a cross section, we know what is the location of your top steel and bottom steel. So we can do moment curvature and you can get your flexural rigidity. But in a member, you're going to put reinforcement wherever you're going to develop tension, depending upon what kind of bending moment profile that you're going to have. So that is again another reason why we cannot estimate this flexural rigidity accurately. Okay, and again we have seen that the modulus of elasticity of concrete is also not linear, right? So if you look at your cylinder stress strain curve for Hawk-Nested stress strain curve, so we get this kind of thing, right? So it is FC epsilon. So similarly, even your IS code, if you look at it, you have a parabolic initial portion, right? So that basically it looks like this, right? So if you see, depending upon where I'm taking the slope, your elastic modulus is going to keep varying. So that is another problem. And also the modulus of rupture of concrete is also, though we write FCR is, what is the value we take? FCR is 0.7 square root of FCK. So this is the value that we use, but this is the code specified value. But you can have variations in your concrete strength along the length of the member. So the variations of modulus of rupture is quite possible, right? In addition to that, you may have uncertainties regarding your time dependent and environmental effects, which is mainly going to come from shrinkage and creep. That is going to keep reducing your elastic modulus, and it is going to induce some additional curvatures which is going to induce additional deflections, which we need to account for that. So there are a lot of uncertainties associated with it. And we are actually dealing with inelastic flexural behavior of members, right? So we are not doing elastic analysis. So this equation, whatever we have learned in structural analysis, is actually valid for when the system is elastic. Ideally, when the system is uncracked, reinforced concrete beam, when it is uncracked, then only we can use this equation in strict sense. Otherwise, this EI is going to keep changing depending upon what is the amount of load that you have applied. Second is, and the deflection itself is a member level property. You can have high variability in your measured deflections. People have measured deflections in the tested specimens in the lab, and you can see that the same set of specimens, when you test it multiple times, you get some variations in your measured deflections for keeping all other parameters same. So that's what we're saying. So even under carefully controlled lab conditions, there is a variability, inherent variability in the measured deflection, because reinforced concrete is a composite system, and you have reinforcement also, it's varying along the length of your member. So these are all the reasons that we need to, we have difficulty in accurately estimating deflections. Okay. So this is another case of a, let's say in this case, we are talking about a fixed beam. You can also have a continuous system with some negative moments at the two ends, right? Let's say for a fixed case, if I start increasing this load W, okay, initially everything will be elastic, it will be uncracked. Then you know the distribution of moments for a fixed beam. At supports, I'm going to develop WL square by 12, right? And then at midspan, it is going to be half of that, which is WL square by 24, right? So these moments are going to not going to change when I keep increasing W. If you give the value of W, then moment I can calculate, right? But as I keep increasing this load, what will happen? The first you will have cracks at this support locations, because this is where I have maximum moment. And you see here we are developing tension at the hogging moment, that is going to produce tension at the top. So you have to put some nominal reinforcement to control this crack. Then if I keep increasing, now the reinforcement will start transferring the load. Then you will have cracks that are forming in the midspan, right? So this moment, whatever that is coming, that can become greater than your cracking moment at this location, then you will develop cracks. So you see here, you have the distribution of cracks are going to be different, and your moment value also along the length of the beam is going to change depending on. Now, if I change this connection as a part of continuous beam, again the moment distributions are going to change. You may have a moment M1 here, M2 here, and you may have M0 here. Okay, so total static moment in a continuous system will always be WL square by 8, but I can distribute something to the support, and then your positive moment can reduce also depending upon the fixity that what you have, right? So now let us see for this beam, if I look at here, how the load versus deflection response. See, again, I'm reiterating, when we did in flexure, the moment curvature, the curvature is a sectional property, right? For a particular section with particular reinforcement detail that we can calculate. So sectional property. But deflection is an integration of curvature along the length of your beam. Okay, so it's a member level property. So, and when the member is becoming non-homogeneous in terms of distribution of steel, then your deflection estimation also quite becoming challenging. Now let us see for this fixed beam how the load versus midspan deflection is going to be, right? So if I start applying the load, so I'm going to, the ends of the beams are going to crack. So that's what we saw. So you're going to have cracks like this, right? And then you're going to have next, as I keep increasing the load, now this you will have cracking here at the midspan. So that's what we saw in the last slide as well. And then you're going to reach its maximum value, right? And this your service load, always you have to see service loads MS will be roughly about 2/3 of your ultimate moment. Okay, and that's why your load factors under service condition we take 1, and when we do ultimate calculations we consider a load factor of 1.5. So you see 1 by 1.5 is roughly, it is 2/3, right? So your service moments are about 2/3 of your ultimate moment capacity. So your service is going to be somewhere here, right? Instantaneous. So at this location, because of this applied load, you're going to get some instantaneous deflections in the service load. Now, if I keep the same load, okay, so this is your instantaneous deflection. Let's say delta I. Okay, but if the load remains constant, doesn't mean that the deflection will remain constant. The deflection will start increasing and it will go to this point. So these are called as long-term deflection due to service. So again, why does it happen? Because of the creep, because you're in a cross section. If you look at it, depending upon the moment distribution, you have sections that are subjected to compressive strains. So you can see that then the concrete will start creeping. So that means the strain will keep on increasing when the load remains constant. So you are going to have additional curvatures that I need to account for in my calculations. Now let's see. So then what happens is if I keep increasing the load again, then you may have reach its yielding. That means the steel is going to yield. In this case, you're going to have yielding first at this support regions. That's where you're going to first you'll have maximum moment. Then if I keep on doing it, then you may reach ultimate load capacity of the member and then you may lead to failure, right? So these are the different stages, okay, of failure progression. In this case, we have taken a fixed beam, okay. Depending upon the fixity, again, this performance, load deflection performance will change. Again, it is also a function of how much steel that I have put at different locations, right? Now, so for example, I think this is one of the examples that we have done in your moment curvature analysis, 400 mm by 600 mm with some steel. This is a heavily under reinforced section, if you remember the module 5 that we have discussed. Now, when I do the sectional analysis, now let's see what happens. So initially, everything will be uncracked. Okay. So you can take, in fact, the steel can be converted into an equivalent steel, the concrete area, and you can calculate EI transformed. Okay. But the amount of steel that what you put is very, very small. So we can approximate that to EI gross. Okay. So that's what we do because the amount of steel is so small, the transformed area of moment of inertia will be nearly equal to that of a gross moment of inertia. So we use for simple calculations only the gross moment of inertia. So your uncracked stiffness will be like this, right? It will be like this. So moment initially, right? Now, of course, if I keep on increasing your, we did the moment curvature analysis. So what will happen? Soon after this cracking, your stiffness will degrade and then it will become like this. And then this is, you will have yielding, right? And when I do calculations of moment, let's say for this moment, I want to calculate the curvature. So you will find that this is your curvature. Similarly, if I keep increasing the moment and I try to calculate the curvature, now at this point, you will find that this is your curvature, right? When M2 has become more than M1, so you'll see that. So what happens to this slope? Initially, this was a slope. Initially, this was a slope for uncracked, and this is the slope. So the slope of this moment curvature curve is keep decreasing with increase in your moment, right? So that is what we have. So when it becomes this point, okay, when it is yielding, so you find that here, so roughly here, this is your cracked moment of inertia. That's what we are going to have. So that is going to be a cracked moment of inertia. Your EI is going to keep reducing depending upon the amount of moment. If moment is less than M cracking, I can quickly calculate my curvature as M divided by EIG, gross moment of inertia, when your M is less than M cracking. Okay, right? So again, when M becomes more than M cracking, I cannot use this EI. EI is going to evolve, or in other words, E is not going to change much, but I is going to keep decreasing. So I have to do the proper calculations to find out what are my. So your actual flexural rigidity, whereas the slope of a M by I is going to be somewhat in between that of what we are going to have between uncracked and cracked flexural rigidity, right? So that is what we're going to see. See, this is what again another form of representing. So the cracked beam is going to start losing its strength as the amount of cracking increases. If I start plotting the flexural rigidity versus the applied moment, okay, when m is less than, when m is here or here or here, your flexural rigidity is going to be uncracked flexural rigidity, which is EI. The moment M becomes more than M cracking, you see here this flexural rigidity value is going to decrease in a non-linear fashion. So this is going to be at location of B, you have cracked EI, which is your, when it is moment has become close to that of yielding moment, then you have reached your cracked flexural rigidity. Okay. So, but in your service moments are going to be somewhere between this and this. Okay. Somewhere here you will have service moment. So that is why depending upon what is the moment that you have here, okay, your E will keep decreasing. Okay. If I am taking moment here, this will be EI. Okay. So in a nonlinear fashion. So that we have to calculate it properly. Right. So this is what we again we talked about in case of a continuous system, which we have seen, because the cracking distribution is going to change, right? If the soon after the beam is cracked by a large moment, it can never return to its uncracked stage. So the moment the beam is cracked, your flexural rigidity is going to reduce and it cannot go back to this uncracked. But in a beam, we know that these are the regions that are uncracked. Okay, for example, this region is uncracked. This region is uncracked. Okay, so at these locations, you will have flexural rigidity will be uncracked flexural rigidity, right? When you have at the cracked, when you have lot of crack at this location, you will have this. Okay, cracked flexural rigidity at this location, at this location, at this location. Now, in between that, you will have some transition. So, flexural rigidity will try to increase also. But what we are saying, for in an average sense, I am going to take an effective flexural rigidity as a function of the moment that what I am considering. Okay, so it is going to be between this uncracked EI and cracked EI. Okay, so it may be here, or it may be here, or it may be here, or here, depending upon the amount of moment that you are going to have, or amount of loading at which you are doing the analysis. Okay, so what we are trying to tell from this thing is, I cannot use uncracked flexural rigidity, or I cannot use cracked flexural rigidity. I have to use something in between. So effective moment of inertia, I effective, should be used in calculation. So we have seen that the E value, okay, the elastic modulus of concrete is not going to change appreciably under service loads. Okay. Now again, deflections, we are doing calculations at service loads. Under service loads, E, at least for short term, it is not going to change. It will change, it will not change much. So the major problem is coming from this I, which is the moment of inertia, right? So that is the reason for to calculate your effective flexural rigidity. We are going to say that E is there is not going to be changing. So you use 5000 square root of FCK and you can take that as E. However, I effective is going to be used in the calculations, not the I uncracked or I cracked. I would use I effective. It should be equal to the effective moment of inertia associated with the maximum past moment. Okay, or in other words, the beam might have been subjected to a temporarily very heavy load. That means it might have already cracked the beam. So you have to use what is the maximum moment or load that particular beam is previously subjected to. Now the service load may be lesser, but in the past, if it has been accidentally overloaded, then it would have cracked. That is the moment of inertia. Actually, we should use to calculate the current deflections for the current applied load. But often we will not be knowing what is that level of maximum moment that particular beams are were subjected to, right? So, but what we are trying to say is, okay, we'll use effective flexural rigidity and use.